Some functions have what are known as inverses. Now, not all functions have inverses, but some functions are what we call invertible functions, which do have inverses. So in this video, we want to unpack what does that mean exactly and some of the things associated with that. So before we get into specifically inverse functions, let's just refresh our memory for a minute. What does it mean to be a function, or what is a function? Just kind of the basic concept. Well, the basic idea is this. You can think of functions as kind of like machines, right? Where you take a quantity, it's usually like an x value, you plug it into the machine, and the function's going to change it. Maybe it adds 2, maybe you multiply it times 3. You do something to it, and out comes a different number. So what we have here is something called the domain. These are the values that you plug in. Then some function changes it, and you get a new value out, possibly. So we'll just take a simple example. Maybe there's a function that when you plug in 2, it'll give you the number 5 as the answer, right? Or maybe if you plug in -1, maybe it would give you +2 as the answer. When you plug in 7, maybe it gives you the number 10 as your new value. So I tried to make this one very clear what I was doing here. How do you think we're getting from these inputs to these outputs? I made this one very simple. This function would be the function f of x equals x plus 3, which in effect what I'm doing is I'm taking these x values and I'm simply adding 3 to them. Now these functions can get very, very complicated, obviously, and we know a lot of these complicated functions. But you can take any x value, add 3, and you've changed it, and you've got a new y value. And this set over here is called the range. That's the y values that come out of these functions. Okay, so we know all about functions, or I'm going to assume that we do. We know about the vertical line test. You're probably familiar with that. That's a test, graphical test to see if something represents a function like x plus 3 or whatnot. But that's not really the focus of this video. This video is about what are invertible functions. Well, here's the basic concept behind an inverse function. I want some function that goes against the grain to where if I plug in a 5, it would tell me it came from 2. I plug in a 2, it would tell me it came from a -1, or a 10 would tell me it came from a 7. In effect, these things are tracing their way back to the inputs that they came from. That's the idea of an inverse function. So for the inverse function, the domain of the inverse function would actually be the range of the original function, because you're going basically like from right to left, so to speak. Okay. Now, before we get into any of the math, where on earth might you see these? Well, here's a great example to help you wrap your mind around, the idea of where these might be used. Whenever you buy something online, so let's say you're going to buy a book from a certain website. Well, when you purchase your book, you have to enter in your credit card information. Well, when you do that, that can't be transmitted online very safely. If they just send it online to the bookstore, somebody could take it and use it and, purchase other things with it, basically steal your credit card number. So what's done is they encrypt it. And encryption is nothing more than running your credit card number through a function, so that even if somebody gets this new jumbled up code, or this new number here, it's not usable to them because it's not actually your number. And so it's in not a usable format. But the bad news is the bookstore that you're buying your book from gets this jumbled up number that you would think of as the output of the encryption function. So how do they know how to bill you? Well, what they do is they decrypt it. In other words, they use the inverse function to figure out, hey, what credit card number did this come from? And there's a secure way that that's done. The current encryption process uses large prime numbers, that we're not really going to get into any of those details or anything like that. But the idea is very simple, and I know this is an oversimplification, but just go with me for a minute. Perhaps they could take your credit card number and simply add 3 to it. Now, I know we would never do that because that's a little too simple, but you can get the idea, though, that what's then made is a new number. Now to decrypt it, what would we need to do? Well, we would need to subtract 3 to get back to the original function. So that kind of hints at what the inverse function of x plus 3 would be. The notation, we write f to the -1. It's not a power, it's a notation. We put a -1 in the upper right-hand corner of the function little f of x, and this means in English the inverse of f of x. This would be simply x minus 3. So if you plugged in a 5, it would come back to 2. If you plug in a 2, it would come back to -1. Plug in a 10, it would come back to 7. This is the inverse of x plus 3, and these guys are inverses of each other. They're inverse functions. Okay, so that's the basic idea of an inverse function. Now there is a catch though. The catch is that if you trace back any of these y values for something that's already been run through the original function, little f, it must come back to the original function. And that's not that obvious, right? So in other words, if you run 2 through f of x to get 5, and then you take 5 and run it through the inverse function, it comes back to 2. Hooray, great, that's awesome and everything. But this forwards backwards idea has to work for every number on Earth. Okay, so it doesn't matter if it works for these 3 examples. If there's another example out there that when you run the x value through the original function and then that value through the inverse, it goes somewhere else, the whole thing falls apart. And I'll show you an example of that in just a minute. Okay, so basically when you compose these 2 functions, forwards and backwards, you should get the original back. We should get the original input back. And you should be able to compose them either way and get the original back. Okay, so here's a simple example to begin with. Let's say we don't know if these are inverses. We want to examine this. So you don't write f inverse until you're sure that they're inverses. So I've got one function called f, x plus 2, another function called g, that's x minus 2. Are these inverses of each other? Well, if you take any x value and you add 2, and then you take that quantity and turn right back around and subtract 2, I think it's fairly clear without a lot of algebra that these in fact would be inverses of each other. So these are inverses. Okay. How do you show this mathematically? Well, if you take f and compose it with g, in other words, you take one function and stick it inside of the other, so we would do not x plus 2, but x minus 2 plus 2. You're composing these, you're running x through both functions. X minus 2 plus 2 reduces to just x. Good for us. I'm not going to take time to do it, but if you compose them the other way, which we should also test, g of f of x, this would also be x as well. So you get the original back. All right, now here's a trickier example, and this will really test how well we know inverse functions, or understand inverse functions. You have a square root function and you have a square function. So you take a function, a number like 3. 3 squared is 9, and the square root of 9 comes back to 3. These seem like inverses, but it turns out, and this is going to confuse us for a minute, these are not inverses. And I picked this example on purpose. So let's think for a minute. Why would these not be inverses of each other? Think about that for a minute. Well, the idea is this. It's very subtle. It was this caution I had up here. When you compose these two, they must equal x for every input possible. And so here's what I'm thinking of that makes these not be inverses. Take something like -4. -4 squared. So let's take g of x first. So -4 squared would be 16, right? Would be 16. But then run that through the other function. What's the square root of 16? It comes back to 4, not -4. So now this is maybe a practical example of how this would break down. Imagine buying a book off the internet again. We would never ever want to have bought a book and it encrypt our credit card information. It gets sent to Amazon or whoever that you're buying the book from, and that turns around and bills somebody else. We would, well, I guess that wouldn't be that bad, but we wouldn't want the reverse to happen, of course. We wouldn't want somebody to buy a TV and then their credit card get encrypted, but then when it got decrypted online, they would bill us. We wouldn't want that to happen. Every person needs to be billed for their own purchases, and so that's why this would be such a massive failure if this forwards backwards idea failed even for one or two or a number of persons. Okay, so these are not inverses. Now, how do you see that? Because it looks on the surface like if you compose these two guys, it looks like you would get x, but in fact you don't. If you take g of, well, let's take f of g of x. If we took f of g of x and compose these two guys here, this would be the square root of x squared, right? Not the square root of x, but the square root of x squared. And whenever you take a quantity and square it and then take a square root after that, it's going to be forced to be positive. So in fact, this is by definition the absolute value of x, which unfortunately is not x necessarily. For positive x's, it is x because the absolute values are negligible. But if it's a negative x value, we're in trouble. So you could do this. Here's a slight modification we can make. Let me erase all this stuff. Okay, we erased all this stuff here, and we made a stipulation before we began. We said let f of x be this and g of x be this, where x is greater than or equal to 0, just considering the positive x's only, then they would be inverses. Okay, so sometimes we can restrict the domain. We can restrict the domain to force them to be inverses if they primarily are inverses but maybe have a few bad spots. Okay. Now there's a lot of other things we can talk about in regards to inverse functions. I'm not going to include all of that in this video because it'd make it really long. In one video we're going to look at a graphical interpretation of inverse functions because there's this neat graphical relationship with the x's and the y's. Think about it. 3 squared is 9. So it would contain the point 39, but the square root of 9 comes back to 3. So you have this interesting relationship between xy versus like yx, if you will. So we'll have a video on that. We'll also have a video on an algebraic interpretation of inverses. Can I just hand you a function, no graph, no nothing, and you come up with what the inverse function is for that given function if it has one. So we'll take a look at that. And then if you're watching this video and you're specifically in a calculus class, then I know exactly why you're watching this video. We study a lot in calculus the exponential functions and the logarithmic functions, specifically like e to the x and like natural log of x. And so it turns out these two functions are inverses of each other. So typically there's a section in every calculus textbook that talks about inverse relationships for the sole purpose of understanding a deeper relationship between e to the x and natural log of x. So if you're watching this video for that purpose, we'll have a separate video on that as well.